So today I propose to have a two times presentation. So first I will present you my research institution in Nantes and the work we are conducting in my team. And then I will move to the scientific seminar related to a problematic of simultaneous localization and mapping. So some works I did with one of my PhD students some years ago. So I will show you the main results we obtained at the end of this PhD thesis. And that was a PhD thesis jointly supervised by some people from ONERA and DGA in France, which are the Army ministry. So there is a link with that one. And especially this SLAM work is related to a collaborative SLAM. So I will center the presentation around the communication aspects and what kind of message we can exchange between the robots to improve mainly the localization. I will show you some results about the mapping, but that was mostly for localization. Okay, so here are some points about, so I don't know if you are familiar in France how research is working, but basically the research is conducted within labs, we call. So here my lab is located in Nantes. So you have the city, so you have the map there, and Nantes is the west, on the west coast. Is the city number 6 in France in size of population. And basically the lab is what we call a joint research unit, and you have all the institutions that are related to this lab. So it means that people from several other schools of engineering and universities, and also institutions like INRIA and SIRIS, they are all together in the same lab. But the lab is multi-site. So basically we have 5 different places. Okay, so it's a decentralized or distributed lab. So basically it's 500 members, and the center of what we are doing on the scientific background is related to cybernetics, computer science, and information technologies. Okay, this is basically what we have inside. So within the 500 members, you have more than 200 teachers, researchers, and full-time researchers from CNRS and INRIA, and about 250 PhD students and postdocs, so mostly PhD students. And we have a technical and administrative support, so about 35 people working in this area. So the lab, there is a very specific matrix structure in which you have the what we call the research clusters with the main research topic, and you have the transversal themes, which are mainly related to the applications about the research. So you see this is from the research part. So we have 5 the main research clusters. So one which is mostly related to automation and control. So this is the cluster about robotics. So I'm leading this cluster. So we have inside 4 teams. I will give you more details afterwards. One team, one cluster which is working on data science and decision making. So this is mostly people working in artificial intelligence with several different applications. There is another one linked to signal and image processing and language processing as well. And the last one is mostly related to software engineering. Okay, so this is basically the structure, and you have the classical, I would say, application related to digital sciences, ranging from digital cultures to vehicles and mobilities and open education and so on. So this is quite usual. So now, if we focus on the robotic activities, so basically this cluster is about robotics, manufacturing, and computing. So you have 4 teams. But there is one team which is more related to the computer science aspect, so we have some link with them, but they are more working on developing algorithm for high-level computing with application on control, design, and robotics, but they are more related to math and computer science. So basically, for the robotic activities, it's about 40 permanent staff, and we have about 50 PhD students. So basically, you have three main teams related to robotics. So one which is working on robotics, so bio-inspired robotic, I would say. So they are making design about locomotion and robotic system and cobotics with human-machine interaction, and robots which are bio-inspired mainly by animals. The other team is ROMAS, so this is mostly the application to industrial robots. So they are designing, for example, large-scale, so they call it XXL robotics, so large-scale parallel cable robots, and also cobotics, but they have strong activities about smart manufacturing as well. And finally, in bold characters, so this is my team, the ARMEN team. So in ARMEN, we are working on the design and control of robots, interacting with the environment. So basically, we are working on eco-design, because here the meaning of environment is both where the robot is evolving, but also the ecological meaning of environment. So how you can design robots that have less impact on the environment. So one colleague is working on eco-design, for example, building some robots in wood, in which the bodies of the robots are fully in wood, and so how you can guarantee the precision and the speed of the robot if the bodies are in wood. So it will change due to humidity and so on. So he's developing controllers and specific design of the robots in this area. We are also working on flying manipulators. So basically, you have several UAVs, and they are rigidly linked together, and they have some manipulation tasks to execute. So how you make the coordination of the UAVs in that point. And finally, this is the topic on which I'm working, which is the autonomous mobile robots, and I will give you more details just now. So if I focus now on the research on autonomous mobile robotics, so basically you have the list of the members. So there is me and two colleagues, Elwan and Olivier, and we have one research engineer. And basically you have here the list of the 7 PhD students working on the topic. And what we address, so it's, I would say, the very general topic of autonomous mobile robotics, ranging from multi-sensor perception and data fusion. Basically, we address both of them, graph-based fusion and learning-based fusion as well. So SLAM, this is what I will present today. So the SLAM we are working on is both the active or passive SLAM and mono or multi-robot. And we have several activities about scene understanding with a focus on multi-object detection and tracking, and also some work about navigation and uncertainties, and with still the research topic linked to decision-making and risk assessment. So here I can show you just, so there is some ongoing works and the platforms we have. So here, for example, some work of one of my past PhD students, we were working on a moving object detection using event-based cameras. So he developed some deep neural network and some fusion architectures based on spiking neural networks to make detection of fast-moving objects using this event-based camera. So this is some work we have done. Here, this is the work from one of my PhD, Charlotte, who is working on multi-robot navigation. So she's just starting the work, and maybe we will do the project with Charlotte, so she can come here also to work on this topic. Another of my PhD student is working at, so I don't know if you can see clearly, but this is a boat here. This is what we call an energy ship. So basically, this one is an artist view, but we have a small scale model. So basically, you have the boat, and it has some flatteners, rotors, so you can control the speed of the robot and the direction. And you have some underwater propellers that will be used to make the electrolysis of the water and generate hydrogen. And from this hydrogen, this autonomous ship will go to another place to deliver the hydrogen and then go back autonomously to make this farming of hydrogen. So we need to optimize because the flattener rotors are using part of the energy you are generating here. So we need to make the balance between how to autonomously control this robot based on the wind, the waves you have, and so on. So Giovanni, one of my PhD students, is working on the control and navigation of this kind of robot. And here you have the platforms we are using, ranging from small-scale robots, the robots we are using. We have also one Scoot, and we have two robotized electrical vehicles from Renault car manufacturer. So that's it. I can show you some, before to start the scientific talk, I will show you a video on some application we have done so far. So it's in French, so that doesn't change the content of the vehicle. So here we developed some, so this is the site of Ecole Centrale de Nantes, the campus, and we developed some platooning techniques with our vehicle. So the first one is manually driven, and you have the Zoe, which is driving autonomously, and you have the second one. So this is the interface we are using for the mission. And so the two autonomous cars will follow the manually driven first one. So here, this is just exchanging position by communication, so GNSS position, basically. So it is a classical, I would say, control approach for platooning techniques that has been done within one national project with partners INRIA, SIRIS, and Ecole Centrale de Nantes. So we also developed some autonomous parking algorithm, which are not path planning based, but sensor based control here to make the autonomous parking. So the vehicle is detecting the autonomous the free places, and then we make this autonomous parking. So this is another project in which we developed one SLAM, LiDAR-based SLAM. So this is for containers manipulation, so very large-scale ones. So you have this kind of robots, the Vasco robots, and we developed this LiDAR-based SLAM algorithm in some environments where they are very changeable. This is some agricultural application for some robots to feed animals. So here we just developed the navigation stack, and also the mission map we developed, so where the robot has to go, and then we make some sensor-based control. So here, this is the iCar simulation we developed for our vehicle, which is growth-based. And here, this is, we replace some data for underground navigation. So we're just testing the SLAM algorithm with underground part. So students can develop on this simulator, and then we can plug directly on the vehicles. So this is some of the, can show you, yes. Stop. Yeah. So here I give you an example of the vehicles because we make by our own the robotization of those vehicles. So this is some drive-by-wire kit, and we also make it for other labs and universities. So that's very useful because for some national projects, since we are almost working with the same teams, we all have the same platform. So ROS-based platform, and we know how they are robotized, so it's more easy to focus. The only point is that we don't have any collaboration with Renault car manufacturer, so we did some reverse engineering with it, so Renault doesn't like really this, but anyway, we have to work and to progress. So the main issue we have is that when they change the generation of cars, we have to adapt the robotic kits because they changed the message, the CAN message, just changed many things. So that was, yes, quite challenging, but then different solution. We also work with Technalia on some SLAM approach for power plant surveillance. We had some application on autonomous vehicles for agricultural application with Manitou, which is a manufacturer of this kind of vehicle, and some last mile delivery application with some partners. And we have this system just to show you. This is a LiDAR plus IMU and multi-camera system. So this is our mobile mapper system. So when we need to build a map, we just have to put it on the roof of one vehicle. We go on a site, we build the map, and then we can perform our localization algorithm for the navigation. So it's very fast and easy to do. So that's it, just to give you an overview of what kind of platform we have and the application. Okay, so now I will move to some results we have obtained. So I will talk about SLAM. So basically, I imagine that most of you know what is SLAM. So I will not go in much detail. So you know that this is widely studied in the literature. So there have been milestones in this work, for example, of SLAM approach, and you have, for example, Vincent, obviously from colleagues in Switzerland, DSO as well. And basically, what is done in SLAM is that you have classically the front-end process, and one part which is very interesting is the loop closure detection part. This is what we will be using here. So this is a state estimation process. So we have to estimate both the map and the trajectory. And the backend process will work on some probabilistic models and make the global inference to get the hidden variable estimation related to the map and the trajectory. And this is based on usually multi-sensors architecture. So in this work, we focus on vision and IMU. Okay, so this is basically what we do. So the work is very close to the Vincent approach with an extension to multi-robot. So the first things we had to develop in this work was the global architecture of the overall system. So the overall system is containing all the different robots. So basically, we discuss on the main process we have to focus on. So you have them. So you find here the classical module of SLAM I just showed you before, and how we will be able to work with multi-robot architecture. So basically, when you have your several robots, basically we have three main stages. We need to have some task and data allocation scheme. So how you will work on the different tasks. Is it a centralized approach? Do you have a main computer that will make the calculation and send the order to the robots? Are you doing this decentralized in a way that each robot is capable of computing its main SLAM and then exchanging approach? Or do you want to move to distributed one in which the computing is also distributed over the different robots? So this is the first question we have to answer within this global architecture. And then we move to the communication policy. So what will be exchanged between the robots based on the configuration of the network, and what will be the schedule of the data exchange. And finally, since the robots, they have to improve their own localization, we need to find a way to do that. So basically, we work on inter-robot loop closure detection. So this is what we call the matching strategy. and the multi-robot data fusion. So the matching strategy is how to make the detection between inter-robots. And the multi-robot data fusion is how to improve the individual localization of the robot based on the data you will exchange. Okay, because this is not an easy task, and especially if you talk about data incest. So to avoid refusing the data you have already provided from the robots. Okay, so this is the question we need to answer. So this is the first design of the system we had to think about. So Rodolphe, as a PhD student, started to develop the global architecture of the system. So then to decide which kind of architecture you choose, centralized or decentralized, of course, there exists a lot of work based on that. So for collaborative SLAM, you have the pros and cons of the different approaches. So for centralized, I will not go in much details, but there is the co-SLAM approach and more recently the CPI SLAM. So what is interesting in centralized approach is that you have all the robots that are mapped, in fact, inside the server. So it's more easy for the resource allocation, but of course, all the robots are dependent from the server. Okay, so that's the main point of centralized architectures. And then you have the decentralized one. Of course, the architecture is more flexible, but then you have a limited autonomy due to the distribution of the robot and their own computation capabilities. But again, there exists a lot of work related to these decentralized architectures. Okay, so basically what we try to solve in this work, so we focus on the three main constraints we highlight from the collaborative SLAM. So the first one is related to what we call the information constraints. So here we think about what information to be transmitted in order to make autonomous detection of inter-robot correspondence, and then to have a consistent estimation, re-estimation of the trajectories. By doing that, for the transmitted information, we have to follow the network constraints. So the network constraints is that the communication policy have to work with limited bandwidth, and for example, communication loss, communication loss between the robots. And of course, you have to focus on the resource constraints. So how to manage the multi-robot interaction, because you need to have some process working. And so it's not, you don't have to divert the resource from other fundamental process from the work, for example, the task of navigation or the local staff approach. So what we did is that we designed a visual-inertial data sharing method. So this is what I will show you in more detail, that will promote the robot autonomy while satisfying those constraints. So this is what I will detail. Okay, so a little bit of theory and maths we did behind. So basically what we do is that we use the probabilistic modelization using the factor graph, which is well known in the SLAM community. So basically the input is that from the robot, we imagine that all the robots, they have embedded IMU. So we have IMU data, so we can reconstruct the trajectory from IMU measurements together with vision. Okay, they have camera. We don't use LiDAR. We just use camera and IMU. And every robot has its loop closure module. Okay, so we can use one point of SLAM, for example, or this model. So basically, from those inputs, we build the visual-inertial graph. So you know that here, the circle, so what we want to estimate are the poles of the rod, so the 6 degrees of freedom. We have the inertial states based on the accelerometers and gyro measurements. And we have from the vision, the landmarks position. Okay, so the feature points, the 3D points that based on the camera model you have, will be reprojected on the image to calculate the residuals. And those residuals, those measurements are here as the factor that will link the states together. So you have two kinds, the inertial factors, so this is what we measure, and the visual factors. And basically what we do to simplify the thing is that we assume that all the uncertainties we manage here will follow Gaussian laws. Okay, so this is basically what we do. So it will allow us to work on the maximum a posteriori estimation problem. Or if you don't have any a priori from theta, your hidden states, then it's a maximum likelihood estimation. So that's very classical. We only rely on existing work in this sense. So the factor graph is that the a posteriori estimation you will generate is just the product of the individual factors we have within this graph. Okay, so this is very classical. So we start from this. But then we will see how we can manage these two multi-overlap. So just it's a lot of equation, but that's not the purpose of this one. What is important here in this kind of graph-based SLAM approach is that the factors here are linking those two states relatively. Okay, this is not absolute measurement, but that's relative measurement. So the residuals error we will measure are relative error. So this is just what I'm mentioning here. So basically, this is what I told you. So the likelihood we will use is under Gaussian hypothesis. So in fact, the factors will be probabilistic constraints between the states we want to estimate. And this kind of problem can be solved easily as a least squares optimization problem. So this is what is done usually within the graph-based SLAM. But then, in order to build those residuals, so those relative measurements, which are linked to position, orientation, and speed from the gyro accelerometers and so on, we need to have some nice representation to do that, to express those relative measurements, and then after to be able to differentiate, so to build Jacobian matrix on those measurements. So to do that, we rely on the work from Barefoot and Sola for the Lie group parameterization, which is again quite usual. So this is the equation you have and the different operators. So for example, to build the relative inertial factors, we rely on the Lie group algebra to build those relative measurements, and then to be able, after, from those vector matrix representation, to make the derivative and compute the Jacobians to make the uncertainty propagations. Okay, so that's just to tell you what we are using. So that's well known, I would say. So if you are not familiar, you just rely on those two papers and books, and then you can have, we are able to design the inertial factors like this. Visual factor, you know, it's basically the reprojection error. Okay, you have 3 points, you back project using your camera model, and you have the error. So basically, that's visual factor, inertial the same. And we have the relative pose factor. So this is the global one between two pose states. Then we have to compute the error between those two states. So of course, you have to do it properly, because when you do this relative estimation, for example, for rotation, you have to be sure that it's still a rotation. Okay, so this is what guarantees the Lie group algebra. So this is what we are using. Okay, so here, this is the choice we have made. So based on the literature, we have a kind of hybrid architecture between the 3 robots. So in fact, it's a decentralized approach. So each robot has its own SLAM capabilities. But then, since they rely each other on the inter-robot detection, it's a weakly distributed allocation. Okay, so this is what we, because we have to rely on some database for the image correspondence when we do the closure. Okay, so this is why it is weakly distributed. Okay, so about the communication policy. So classically, what appears in the literature is what we call a two-tier communication policy. So you see that in the when you have the two robots. So for example, one robot is requested the keyframe and it has its current knowledge of state, and then the robot will exchange what we call the packets. So I will show you how we compute those packets. So we have two kinds of policy in communication. One which is the regular policy, in which on request, one robot will send the visual inertial packets, the correspondence between features, and the requested keyframes. And in order to correct the estimation, there will be the regularization policy, which is this time delayed, and that will contain the same element from the packets. So basically, I will show you how we build those packets. So here, the inter-robot correspondence is quite classic. We use bag of words approach from a visual database. So when you have a new key image, you have two different stages. Within the robot, within its own SLAM, it will make the intra-robot detection, okay, to make the closure and to improve its own SLAM capabilities. And then we have the same process, but for inter-robot. So if the robot on query at a given time is able to find nearly the same place, then it will request from the other robot to exchange some data. And then this is where we will run the global inference to improve the individual localization. Okay, so this is basically what we realize. So we need to have access to an external database with visual memory. Okay, so here you have the single robot. So basically, for multi-robot inference, when we will run the estimators in order to improve the individual localization, we just extend the classical, I would say, single graph factor to a multi-robot graph factor. So in fact, that's quite easy. We just link the state when there is an inter-robot detection. We just link the different states from which we have the detection of the image by a new factor, which is an inter-robot relative pose factor that will help us to estimate the transformation between those two robots at those two time instants. Okay, so once we get this, we can run the global inference, and hopefully it will improve the localization of each robot. Okay, so here we discuss. So I will not go in much detail, but basically the work of the thesis, and also this is what we published in RAS 2022, is that we developed three different kind of approach for generating the packets that the robot will exchange to improve their localization. So there is one, this is the one I will detail because this is the one that works the best, which is condensed visual-inertial packet one. But we developed another one, so from the most classical one, which is submap exchange. So basically, each robot has built its own map, and then you exchange the features from the map, and then you improve the based on some co-visibility criterion, you improve the localization. So this is one classical one. This one is again based on what we call the pruned visual-inertial packet. So that's a different approach here for the uncertainty propagation and how we build the packets. And then you have the final one that I will detail now, okay, for the condensed visual packets. Okay, so how we build those data packets that will be exchanged between the robots. So basically, once there is an inter-robot detection, there will be a query of the submap part. So the submap for us is a subgraph. Okay, so you have the proportion from which two time instant, the robot wants to improve its own localization, and it has a detection from another robot. So he said, okay, now I want you to send me the data, and I will run the global inference. So then we will improve both our localization by exchanging the data. So from those time instant, so in time and space, we extract the corresponding subgraph. Okay, so each individual robot is building its own graph. So once they agree on which part they have to exchange, they exchange this subgraph. Okay, so that's a part of the graph we cut from each individual robot. So once you do that, since this is only relative measurements, then you lose the global reference in that case. Okay, so we miss the global reference frame. So what we do is that we will then fix the first frame by running a local bundle adjustment approach classically, and then we will be able to make some gauge fixing on the first states of the robot, as it would be the starting of my slam process. Okay, so we fix it. Otherwise, if we don't do that, we don't have any reference, global reference between the robots, so the optimization process will be lost. Okay, so this is what we need to do. So basically, this is what we do with this symbol. We fix, in fact, the reference here by running a local optimization, which is a local bundle adjustment approach on the visual part. So once we make the re-estimation with an initial state, this is an initial pose, then what you can see is that we, from the two robots, we forget the future states, or the states we have estimated. So both past and future states are forgotten. Okay, so we just cut the graph, so we miss the parts of the whole graph the robots built before. So in order to get this information, you cannot just cut a graph like this, because you will lose the information from the past states and the future states. So we need to do what we call marginalization of the random variables. So this is what classically is done. So what we do here is that we will, in fact, condensate the information, because the marginalization, if we take the states like this, we cannot send the whole graph. Okay, it's too heavy. But we cannot still send all the factors, including, because here this is a representation with few states, but it can be 1,000 states. It depends on the frame rate. So there will be too many factors to be sent in a packet, so it's impossible. So we have to condensate the information. So one way of making the condensation like this is to make local marginalization. Okay, so basically, this is what we do here. So you have the Gaussian representation of the probability distribution. So basically, this one is estimating the pose based on the Visual-Inertial measurements. And at the top, this is the overall estimation process, including the pose and the visual and inertial measurements. So basically, when you do, I don't know if you are familiar with marginalization, the main problem is related to the covariance matrix. So basically, marginalization in those states is that in the covariance matrix, I will just suppress some line and columns. Okay, so if you do this like this, you lose the structure of a covariance matrix. Okay, that should be certainly definite and so on. So to do that, the best technique is to make use of the Shor complement, which is quite well known in marginalization of a probabilistic process. So basically, this is how it works when we want to condensate the information. So all those states will be all represented by the same absolute pose factor. So we can compress the information. Once we make the representation, so we say, okay, in our global state, we just selection a few variables. So it means that, for example, if you have in your concatenated states several frames of several pose, and I just want to keep the first pose and the last one, I have to delete all the pose between. So it means I have to delete all the lines and all the columns of the covariance matrix like this. So I cannot just suppress it. I will make the marginalization process. Okay, so this is what we do. So here, this is not the formalization of covariance matrix, but we use the Fisher information matrix. So this is why you have this formalization. So based on that, we have a local marginalization. But when you do that, it's not sufficient because this will generate then you will start from a dense covariance matrix, and making the local marginalization will create correlation between the random variables. We don't want that because if you keep like this is, you will create new information. So virtual or bad information that were not needed at the beginning. So in that case, we need to rebuild the covariance matrix in a consistent way. So this is one of the contribution of Rodolphe. He did what we call a consistent sparsification of the covariance matrix. Okay, so basically you have your original dense covariance matrix. So you don't have correlation at the beginning because all the measurements are independent. Okay, so basically the covariance matrix is block diagonal, so it should have its shape. But when you do the local marginalization, you obtain this one. So how to make this? We formulate this as an optimization problem based on the Kullback-Leibler divergence. So the Kullback-Leibler will give you the difference between two probability distributions. So we want to minimize it. But if you do this just like this, it will not be consistent in a way that you can create new information content that we don't want. So in that case, we just apply what we call on the covariance matrix, the loaner order. Okay, so it is based, so you have the source covariance matrix, you have the target covariance matrix, and basically the loaner order, when you make these constraints, is based on the eigenvalues of the covariance matrix. So in that case, you take the maximum covariance eigenvalue of this covariance matrix, and you take the eigenvalues of this one. So the smallest one should be bigger than the maximum of this one. In that case, you keep the loaner order. Okay, so this will guarantee the sparsification without adding new information in the target covariance matrix. So this is mainly, yes, I would say the scientific contribution that Rodolphe did, because usually people, they just make the Kullback-Leibler divergence measurements, but they don't add the constraint to have a consistent target covariance estimation. So usually it will generate new information, and so there is a new bias in the estimations of the pose and the inertial factors. Okay, so this helps to reduce the bias and the error you have on the final state estimation. Okay, so to make the packet computation, so of course we will add to this previous content of the subgraph together with the Visual-Inertial packets. There will be some keyframes selection based on some co-visibility criteria. So how percentage of the image there is an overlap. So in that case, we select the keyframe. And for the images selected as keyframe for the inter-robot correspondences, we will retain the key points and the visual descriptors. Okay, this is what will be stored after for the report. Together, of course, with the camera model, because we need the camera model in the packets to compute the reprojection error, because you can imagine that between two robots, they don't have the same camera. Okay, so you exchange the camera model to compute the residuals. Okay, that's it. And then from that, we can compute the final packet. So the final packet content, you have, based on what I show you with the local marginalization and the sparsification, we have the new relative pose factors together with the key points and the visual descriptors of the image that close the loop, and the camera model, of course, only in the first packet, because once the robot, they know each other, they don't have to send again the camera model. Okay, so that's it for this first approach with the CDIP approach for the computation. So now we'll show you the results we obtained. So that's not an easy task to make the evaluation because we need some metric of evaluation and dataset to make the evaluation. So at that time, what we did is that we used the EuRoC dataset using some UAVs and what they call the machine hole dataset. But each dataset is an individual UAV, so we simulate multi-robot exploration by mixing the different scenarios. So when you have scenario 1, 2, is that we mix the sequence of machine hole 1 and machine hole 2. Since the robots, all time they will evolve in the same environment, so we can virtually create a multi-robot architecture. So we use the MATLAB system for that software, and then you have the different trajectories. So this is only UAV-based approach. So in that way, we design different scenarios with different distance and durations. So that's the first data set we use. And secondly, with the Onera institution, they have some experimental test area. So we build our own data set, which is called the AirMuseum, which is an open data set that you can download. And then we create this large place. So we make use of both drones and ground robots. You see with the Ecole tag to make the detection of the robots, and some other which are fixed to localize. So you have 10 cube. So this is the square you have here in the environments. And you have the different robot trajectories. So here that was easy to generate the loop closure. So we know which trajectory has more or less loop closures than the other. Because for the EuRoC dataset, that was very complicated to identify where you can have a loop closure. So we designed this one to make the evaluation. Okay, so to make the multi-robot simulation, this is what I told you. So from both AirMuseum and EuRoC, you have the ROS bag. So this is what we use. We run the Vince mono in open loop. We also using the feature, we do the retracking, so we can generate easily the bundle adjustment after. And so with that tracking and the Vince mono, we can already generate the pseudo ground truth of the Visual-Inertial measurements and so on. This is what we save. So basically in the output ROS bag, we have the odometry, the result tracking, and the IMA measurements. So we have all the simulated multi-robot data. And then from the front-end replay, we have all those detection and robots. And then each robot has its own ROS node. And then we have finally the robot logs and the network logs for simulating the application. So here you have some example trajectory on the condensed Visual-Inertial packets. Here, a trajectory, and the other one with submap, etc. Okay, so this is just to show you the main results. So here you have, for example, based on the approach, the packet computation time, it's in seconds. So you see that the pruned one is the fastest approach to the packets, less computation time. And for submap or condensed one, we have more or less the same, but it's still compatible with real-time application. You have the integration time of the packets and some calculation about the post-graph, the global post-graph optimization, and the button adjustment part. Okay, so you see that the different approach, they have different features, but basically the best trade-off here is the CDIP approach that we have been developed, and especially for the packet integration time. Okay, so of course we evaluated the packet size of each approach, and together with the average bandwidth consumption. So basically, you see that when you exchange the submap, you need to have several correspondences to run the ICP. So there is a lot of the packets which are linked to correspondences. And for the other one, this is more related to visual frames. And you have the packets who have more or less the same size. And on the top, you see the representation of what is inside the packets. Okay, so you see for some approach, we have the initial measurements, extra visual features, landmarks, and so on. So we have the parts of the packets that have been built. Okay, and this is, yes, the cumulative exchange timelines, but that's more or less the same, just to see that the CVIP is the one that has the less cumulative exchange time. Okay, so here I just show you the results we obtain on the translation errors on the estimated trajectories for the EuRoC dataset. So basically, the red line you have here is the mono-robot estimation. So what we can see there is that on some scenario, we build on EuRoC. For example, we hold the approach by making the multi-robot SLAM are better, so we get less errors in translation than the mono-robot case. So that's the case, but for some, it's mitigated. You see, for example, this one is not good, this one is average, and especially the submap doesn't work at all, and the other one, they are the same as the mono-robot case. This is because, as I told you in EuRoC, that was quite difficult to have scenarios in which you have sufficient number of loop closure in order to make the detection and to improve the localization. So in that case, this is what we see, except, for example, into the scenario in which you have robot 1 and robot 3, and for improving robot 3 localization. So in that case, it works quite well because in the two scenarios, we have a lot of loop closure possibilities. So that's what we have, but globally, we obtain at least the same results as for the mono-robot case. And here, this is on our custom data set. So that was more easy to get the loop closure, but again, all the scenarios, they don't have the same features, okay? Because some of them will have good loop closures, and sometimes we have too much change of viewpoints between the ground robots and the UAV. So again, the loop closure will fail in that case. So this is what we identify sometimes in this approach. But basically, you see that, for example, the CVIP, in the case of robot B for scenario 3, we improve compared to the mono-robot case. We improve the localization by making the collaborative stuff in that case. And that's the same on some other scenarios, for example, on this one. Okay, but some other, for example, here, you see using the drone, this is where we have a big change of viewpoint. Condensed visual packets, we have problems here in the estimation. Okay, so that's it. So I come to the conclusion, and just before to show you one video of the application of this approach on the mapping. So basically, this is what we wanted to do. So we developed one method for sharing vision and inertial information. So this has been done within a collaborative SLAM architectures. And of course, the idea was to work on the most decentralized and distributed approach in order to improve the robot autonomy in terms of data and process. And the idea was to, of course, take into account the information constraints, network constraints, and resource constraints. So what was interesting here is to work on the loop closure approach between the robots. So this is the detection of inter-robot correspondences. And of course, how you can make a global inference over the multi-robot by making this probabilistic framework. So this is what has been done in the world. So basically, in the approach, so the CVIP and the pruned one, they conserve the information in a consistent manner because they have explicitly the local marginalization and sparsification together. And at the end, the precision we get over the rotation and translation is better for the condensed one. But basically, all the approach, the packet size and the bandwidth requirements are compatible, I would say, with classical network we could use. And the same for the integration and inference time. The calculation I show you are compatible with real-time use. So just to show you some perspective, we are currently working on, but more in an active SLAM framework with Farhan, which is another PhD student. So we continue to work on the packets design, but we are thinking on other architectures. So basically on the images, since even if this is monocular one, we don't integrate the visual constraints we can have between the images. So for example, the stereo or the epipolar ones, we don't use them through time. So that could be used to add some additional factors that we link the different states, and also can be used based on the scale factor with the INU information. And another one here is to improve the different pose factor to fix some of the angles depending on the application. When it is 2D, it will be different from the UAV flying, so we can add new constraints depending on the kind of robots you are using. So this is also what we can use as an extension of the current packet design. So that's it. I can show you the video of the mapping. So this is one extension we published with Rodolphe in EuRoC 3 years ago. So here, this is, you find the same packets generation, but then here, since this is based on the mapping, we have a specific technique to make the mesh computation and what kind of data, how we can build incrementally the mesh. So that was the main purpose of the paper, what kind of data to exchange and what kind of approach for mesh generation. So we use the truncated signed distance fields in that case to incrementally and in a consistent way to build the map. Okay, so again, the tests were done on the EuRoC dataset. So we use for the localization the approach I showed you before, and then we extend it to specific mapping techniques. We show that the map is consistent, and using multi-robot, you can also improve the different metrics. Okay, and this is the end for me. So thank you. Any questions?
Thank you for the nice presentation. It's nice to see that ONERA is still funding this topic. So I was actually working on this topic before EuRoC dataset.
Okay.
Several years before, with ONERA, before ONERA.
Yeah.
Yeah.
Okay, so this is why you are talking about Toulouse.
Yes.
Okay.
They thought that I can solve it in 1 year. I said maybe not. So it's good that they continue funded that.
Yeah. So that was the ONERA Palaiso site.
So I have several questions. Some are high level and some are more in detail. Maybe we take the details offline.
Yeah.
So the high level, basically, each robot keeps a map of, so their own map plus all the information that they gather from other robots, right? So that's the map that each robot is building.
Yes.
And my understanding is that the subgraph that you cut and transfer depends basically only on the bandwidth or some other factors as well. So the size of the subgraph, because ideally you can send all.
Yeah. Yes.
Right? But you can't.
Yes. So this is both. You have the bandwidth, available bandwidth, and you check when you have the loop closure detection if you can then send this part of the graph.
This part. So what's this? That was unclear for me. So you have And also what was unclear is how do they find out that they have loop closure detection?
Yeah. So I forgot to tell you that there is the current estimation, but there is also what we say, what we call a retrospective one. So you backpropagate also the correction in the past, because you detect.
Yes, if you solve the whole graph, so you just append that to the graph and you solve the whole graph, so that's fine. But in a front end, so each robot has its own front end, and then at some point it needs to detect the loop closure with other robots. So to detect it, there are two images overlap. So how do they do that?
So you have a global. This is where you have this. Decentralized.
Okay, so everybody sends data there, and you do loop closure. On
and they will update it once they detect the loop closure. They will send to.
Why don't you do the map there? So it's the same.
Because we want to avoid
because
being too dependent from the server, from the centralized one.
Okay, so it can be asynchronous. Doesn't need to happen when it actually happens.
Exactly.
So that's good. And so still the fraction of the map that you send, it's just dependent on the bandwidth, because you can't send the whole graph.
No.
Okay.
No. And also there is the marginalization process.
About the marginalization process, I kind of thought that that's an elimination process.
Yes, that's it. Marginalization is elimination.
So marginalization is just what you need to do for elimination.
Yes. To do a clean.
And why do you do bundle adjustment if you just do the elimination? So you just eliminate the variables that you don't want. So you have a graph in one robot.
Yes.
And you want to send something from that graph.
Yeah.
And you don't care about the rest. So you just eliminate the rest of the variables. So it's an elimination process.
Yes.
And that directly condense all the information. So in a classical system elimination, you just condense all that information into the chunk of variables that you want to send. So you don't need the bundle adjustment.
So we need just the bundle adjustment to re-estimate this local graph, because you cut it, and since we will fix the reference of the first state.
But the elimination process does that already.
No, you have to do it before, because you need to have a common reference between the two robots. So this is what we call the gauge fixing. So you need it's arbitrarily fixed, but you need to have a common one.
That depends on how you construct. So what do you do with the information then in the other robots? Because you can just use the factors and the solution and rebuild the factor graph. This is what I did back then. So I was just
directly using the marginalization.
Elimination, send everything, construct the factor graph, and solve. So construct a completely new factor graph and solve. And then what I was thinking is, how to do that incremental. And I think now what I'm working with my students here in my postdoc, Ido is my postdoc. If you think in relative, so all those T's are absolute, right? Your variables are in absolute.
Yes.
There are absolute poses. How about relative ones? So I think that's.
So we build the relative factors after we condensate this information. So
no, but that's variables, not having absolute variables, having relative variables. So having actually the transformation between poses as variable.
Yes. So it's a question? Is it? Maybe I don't understand.
It's just a suggestion.
Okay.
It's a question if you did that.
But if you don't estimate, if you don't do the local bundle adjustment with common reference, you don't have an offset for the translation, for example, between the two robots. I would say the overall orientation and the scale.
You close the loop between two robots, so you have that.
Yeah.
So if you close the loop, then you have a link between the last pose of this robot and the last pose of that robot, or whatever pose of that robot.
Yes.
And that's the link.
Yes, and you estimate the transformation.
And you have the prior on the robot that you transfer the data.
Yes. So maybe marginalization is sufficient. Yes. And you just suppress the states when you do you make simple suppression for the elimination.
No, so if you do elimination, what you do, it's basically you do not, so everything that, all the variables that you don't want are recalculated. No, all the variables that you want are recalculated in terms of variables that you don't want, and you fix the ones that you don't want.
Okay.
And I think this is what coming the first reference that you put in the slide of references.
On the
you had some references.
Yeah.
Yeah, the decentralized data fusion SAM.
yes,
Cunningham.
yeah.
So I think he did something similar like that. So he just did variable elimination.
Yes.
And he transferred.
Yes, you can do that, yes, within the state, but then how you manage the covariance matrix in uncertainty. This is where we call marginalization. Because you don't just suppress the lines and the columns of the corresponding states. This is what we did. Yeah.
So you do need the covariance. You do need the covariance, but you can work in information form. So you do the elimination in information form. And you just
Yes, as well. Yes, but you need to this is what we did here. We have the short complement is done within the.
And another easy way is to just send a list of factors and measure them.
Of course, yeah.
And it's not cheaper to do that because anyway you need to solve.
When we made the evaluation, this is what Rodolphe did at the beginning, and I don't know what percentage of improvement we have instead of doing that. I don't have it in mind. Yes, I have to check.
Because that.
But this is what he did at the beginning.
Yeah, that seems to be. Obviously, it's not too fancy. It's just sending the factors through, and you need to decide which factors would improve the estimation of the other one. But from the way you solve the map in the other robot, so the robot that receives, that's optimal. So, on the other hand, in here, you based on how good you could solve in.
But since we don't send all of them and we cut, this is why we need this process. I agree. Yeah. Otherwise, we have to send them all. Yes. Yeah. Sure.
Any other questions? Do we have questions online?
Well, maybe some of a very much more high level question, I guess, is that do you think that, I mean, one of the big challenges with visual SLAM is different perspectives on the same thing. And if you've got like a distributed set of robots that are observing, like maybe some of the things that might be the things that are in between would be much more likely to have very hard to associate, well, not maybe potentially improperly associated, things. Do you think that decentralized would be much harder in this? I mean, it's sort of a similar thing if you drive around something and you have some things in the middle, but with decentralized, is this better or worse, do you think?
That's a good question. In the purpose of exploration, this is what we did here. Decentralized was, I think, yes, one of the best solutions, but after it depends how far also are the robots, because if you never have loop closure, then it's not a good way. So maybe centralize the information, it's better. It depends. But in that use case, that was the best solution compared to what we did in a centralized manner.
And I guess similar, but did you try these things much outside rather than just inside? And
No. It just for instance, we don't test it outdoor. But that's maybe it will change. But we had some issues indoor with the Onera side because we don't have the ground truth with the GNSS since that was indoor. This is why you have the Ecole tags everywhere. Maybe it could have been different with this precise GPS. But of course, outdoor, we don't know how vision is. What are the behaviors?
Yeah, I mean, I've tried some things like applying and not actually doing research in this area specifically, but it's a very challenge. Can be very challenging.
Yeah. Yes. But maybe extension to LiDAR, LiDAR SLAM, LiDAR-based SLAM could be working as well. So loop closure is quite easy as well with the LiDAR.
Yeah.
Another question. Thank you for the presentation. Right at the start, you talked about how the results showed that it improved some of the localization, but not necessarily the mapping part. And then right at the end, you sort of showed the video and talked about how you used like a TSDF and built a map.
Yes.
I was just wondering if you could talk a little bit more in detail about why the map wasn't necessarily better, and if that was like a result of the multi-robot system, or like why you thought the map had not improved.
Yes, so that was the system was a little bit different because we had one RGBD camera. So we had already the depth for the single robot. So the idea was to map faster in an environment. So when you have multi-robot, the idea was to build faster and to have a consistent map. That was the only purpose.
Okay.
But what is the strategy of what kind of information you can exchange, especially with point cloud? We didn't want to exchange point cloud. So this is why.
So you're just relying on successful loop closure to then just improve
exactly
the map in the same way you get a successful loop closure with a single robot.
That's it.
I have a very final question. So in a multi-robot setup, there's a possibility of a robot being observed by another.
Yeah.
And
Yes.
that actually would give you the location of that essentially a prior in the subgraph situation.
Yes.
Has that been considered?
Yes. In the scenario, sometimes the robots they were able to see each other.
Yeah.
This is the problem we had with the EuRoC because when you simulate,
the
you never. So this is why that was very difficult.
And
Thanks so much.